Hello, everybody, and welcome to our tour of the universe. My name is Jackie. I'm a planetarium presenter here at the California Academy of Sciences, and normally we do this program simulcast from our planetarium. However, today is our biannual maintenance. So we are have our engineers are hard at work right now cleaning our projectors, realigning them, making sure our image is nice and beautiful inside. So instead, I get to come to you from one of our conference rooms in at the Academy. And from here, we get to explore our universe. Now, this is one of my favorite shows because it is 100% live. Today, we are using a software called OpenSpace. It's an open source software that you can actually download at home for yourself. It's funded by NASA, and the really great thing about open space is that we actually get to explore our universe in real time. So everything we're about to see is about what we're seeing or where everything is in our universe um, about right now, give or take an hour or two. So to be able to start our tour. We are going to start shortly. And I want to say thank you to everybody who's joining in, including our friends from New Jersey and here on planet Earth. So I'm going to go ahead and take away my camera so we can start our tour. And we are going to start our tour today relatively close to home, just a few hundred miles above the Earth's surface at the International Space Station. Now, the ISS, for short, is as far as humans do physically travel nowadays. You can fit about 6 astronauts on it at any one time, and it is the largest object that we have built in space. Some people like to call it the size of an American football field. I like to say that it's about the size of the Academy of Sciences. So if you've been in our building and walked from one side of our museum to the other, you have actually walked the length of the International Space Station. But today we are going to go much farther from our planet. We are actually going to see how far our human influence has gone. We'll see how far humans have physically traveled, how far our spacecrafts have gone, and how far our human communications have gone as well. But for now, the ISS is as far as humans do physically travel nowadays, though there are plans in the works for that to change. In fact, NASA has its Artemis mission that will be sending the first woman to space, which I am very excited about. But today we are going to go ahead and start our journey to and focus in on our closest natural neighbor. We are going to go ahead and focus in on the moon. Now, the moon is as far as humans have physically traveled out in space. The Apollo astronauts went out here in the 1960s, and it took them about 4 days to get to the moon. Now, even though the moon is close to us, in fact, it's our closest natural neighbor, it doesn't mean that it's close in human terms. The moon is about of a quarter million miles away from us. And today, we are actually going to go much further. We are going to go distances of millions, billions, and even up to trillions of miles. So, when we get up to these large distances, it doesn't make sense for us to use miles or kilometers as a measurement of distance anymore. So, from now on, I'm going to use a different yardstick, so to speak. I am going to use the speed of light, the fastest thing that we know of. Now, if we were actually traveling the speed of light, which is almost 200,000 miles per second, it would take us 1.5 seconds to get to the moon. So we say that the moon is 1.5 light seconds away from us. All right, let's go ahead and zoom on in just a little bit closer to that moon. See those beautiful craters? And as we zoom on in, it may look like the moon has been hit by more things than us, like asteroids, comets, meteors. But remember, the Earth is actually a very big target, so we get our fair share of impacts. Also, the moon has basically zero atmosphere. So there's no weathering, there's no erosion. Also, there's no plate tectonics moving around, so nothing gets erased once they appear on its surface. But let's go ahead and zoom on out just a little bit further, and we'll start to see the orbit of the moon around our planet Earth. Now, it takes the moon about a month to go around our planet just once, or I like to call it a month, because it's actually not quite a full month. It's about 29 and a half days. And we can see that path. And then let's go ahead and zoom on out just a little bit further to see the other objects in our solar system, some of our other planets. Now, all the way out here, we have the sun at the center. Now, if we were traveling the speed of light, it would take us 8.5 minutes to get from Earth to the sun. So it's about 8.5 light minutes away from us. We can also start to see the paths of the rocky planets in our solar system. We have Mercury, Venus, Earth, and Mars. Further out would be the gas giants, Jupiter and Saturn. Even further out would be the ice giants, Uranus and Neptune. Now, when we get this far out, I like to pause for a second and notice a sizable gap in between Mars and Jupiter. Now, we know that there actually isn't that large gap. There's actually quite a bit of stuff in there. It's what we call our asteroid belt. And this asteroid belt has lots of different asteroids in it, but there's one particular object I like to highlight. And I'm going to take a moment and want you to think about what might that object be. So I'm going to go ahead and bring up its path as well. It's kind of in the center of that asteroid belt. Let's go ahead and see if we can zoom on in just a little bit closer to see it. It's going to be a kind of light bluish color. Kind of hidden in between those asteroids. There it is. Now, any guesses on what this actually is? No wrong answers? This is an object we called Ceres. It's called a dwarf planet. And it's okay if you haven't heard of this object before. Many people haven't. But I know you all have thought of another dwarf planet that we have in our solar system, and that is Pluto. And I've brought its path up as well. Now, the reason why I like to highlight Ceres is because it actually has a very similar story to Pluto. When we first found Ceres about 300 years ago, we thought it was the only thing orbiting in between Mars and Jupiter, so we called it a planet. But around the same time, a lot of astronomers started finding these kind of small rocky objects that they started calling asteroids. So, and they changed Ceres category from a planet to an asteroid. Similarly, when we first found Pluto, we thought it was the only thing orbiting out here in the outer parts of our solar system. But in the late 1990s and early 2000s, we found a lot of other objects. Some of them are just highlighted here. Most of them are small, icy objects, but some of them were quite big. In fact, one was about the same size as Pluto, called Aries. So instead of us adding another dozen or so planets for all of us to memorize, astronomers got together and said, well, maybe we need to come up with a specific definition for what a planet is and maybe come up with another category for what isn't a planet. So they came up with 3 criterias of what a planet should be. 1, it needs to orbit a star. Well, both Ceres and Pluto do that, so check. 2, it needs to be large enough, massive enough to have its own self-gravity strong enough to pull itself into a round spherical shape. All right, well, Ceres and Pluto are round, check. 3, it needs to have cleared its path, meaning it needs a relatively clear orbit. Well, as we can see, Pluto goes right through this Kuiper belt, and Ceres is right through the asteroid belt. So that kind of kicks them out of the planet club. But they came up with the new definition, a dwarf planet. Now, I know a lot of people were a little upset when this happened, but I like to think of it this way. Yes, Pluto got a demotion, but Ceres got a promotion. So, pretty neat. Also, we have a bunch of new dwarf planets in our Kuiper belt. Now, when I say we have a bunch of new ones, they were already there. We just renamed them. So I'm going to go ahead and put away our Kuiper belt objects and our asteroid belt objects. They tend to slow down our software, so we'll keep on going. But before we head out of our solar systems, let's recap about how far we have gone out in space. So remember, it takes us 1.5 seconds to get to the moon if we were traveling the speed of light. So it's about 1.5 light seconds away. The sun is about 8.5 light minutes away. And now, if we were to actually go from one side of Pluto's orbit all the way over to the other, it would take us 10 hours traveling the speed of light. So it's about 10 light hours across. Pretty far. But we can actually check in again on our human influence all the way out here. We are going to see how far our spacecrafts have traveled. So what I've brought up, these orangish lines show how far our fastest and farthest spacecrafts have gone. So we're seeing Voyager 1, Voyager 2, Pioneer 10, and Pioneer 11 that were sent out in the 1970s, and more recently, the New Horizons spacecraft, which was sent out to Pluto back in 2015. Now, these are the fastest and farthest spacecrafts that we have sent out, but none of them have actually gone as far as light travels in one day. But let's continue our journey because we still have quite a bit of distances to go. And we're going to start to go in distances of light years. We're going to start flying past the other stars in our galaxies. Now, the closest star to us, well, beyond the sun, is about 4 light years away from us. So it would take us 4 years to get there traveling the speed of light. And even way out here, we can actually check in one more time on our human influence. What I've brought up is what we call the radiosphere. This shows how far our first radio and television signals have gone out into space. Now, the earliest radio signals that were strong enough to escape our planet's atmosphere and magnetic field were sent out in the 1930s. So, this is about 90 light years away from us in all directions, since radio signals are traveling the speed of light. Also, we can check in on how many planets we have found as well. Now, every ring is around a star that has at least one planet orbiting around it, or what we call an exoplanet, a planet outside of our solar system. And we have found thousands of exoplanets so far. Now, if we look really carefully, you can see that there are several planets inside that radiosphere. So, who knows? Maybe there's somebody out there listening to Nat King Cole. I think that would be pretty neat. Okay, we still got to keep on going because we haven't even flown past our own galaxy. We haven't gone outside the Milky Way. And now, as I zoom out, I want to encourage you all to keep an eye on that radiosphere. See how long you can actually spot it. And soon we'll actually start to see the large scale structure of our galaxy. Now, we live in what we call a spiral galaxy. It's pretty flat, as you can see, shaped with these beautiful spiral arms full of gas and dust and stars. And we are about 2/3 from the center of our galaxy. And right at the center, you will see a bright group of stars that are very close together. And if you could look past all those stars right at the very center of our galaxy, you will see, well, basically nothing because there's a supermassive black hole at the center of our galaxy that's about 4 million times the mass of the sun, so we can actually see it. Okay, can you still see that radiosphere? Right here. That's our little corner of the galaxy, our little neighborhood. So now we are up to distances of thousands of light years. From one side of the disk to the other is about 100,000 light years across. So if we took a round trip from one side of the galaxy back to the other, it would take us 200,000 years. Pretty far. Now, our galaxy has about 400 billion stars, but it's just one galaxy out here in our universe. Every dot we see now is not a star, but another galaxy with its own billions and sometimes trillions of stars. And the colors of these galaxies may make it look like somebody accidentally spilled some cosmic Skittles in the universe. While that would be really cool, these aren't the actual colors of the galaxies. These colors represent the different surveys that mapped the galaxies or the different densities of those galaxies, how much stuff is in there. And now we're starting to see that large scale structure of our universe. And when we get this far out, some funny things start to occur. One, it looks like we are at the center of everything. Now, I know a lot of people think that they are the center of the universe. As far as we know, there's actually no center of the universe at all. It's only because of our perspective here on planet Earth. We are the ones that are mapping the universe. So as we look out, everything looks like it's around us. If we were to go to any one of these other galaxies and mapped the universe as well, it would look like we were at the center of the galaxy or the universe as well. It's only because of our perspective. One other thing that is occurring because of our perspective is it looks like our universe is shaped like a bow tie or butterfly. Well, I know the butterflies in our rainforest right across the way would definitely like to know that our universe is the shape of a butterfly. It's not actually the shape of a butterfly. Again, this is because of our perspective. Remember, I told you our galaxy is made of gas and dust and stars? Well, that gas and dust get in the way of our view. We can't see past our own galaxy. So that's why we have these kind of gaps in between. So we're pretty sure that there are other galaxies in those locations, and maybe one day we'll be able to map those. But as of right now, we can't. Now we're going to continue our journey to start to see some of the earliest objects in our universe. And I do mean earliest. These are what we call quasars. They're bright cores of the very first galaxies. Now, when we are looking out into space, we're kind of time traveling in a way because the light of these objects has to travel so far. By the time it travels all of that distance and gets into our telescopes, we are seeing the light of those objects as they were in the past, not how they are today. So we're seeing the light of these objects as they were years ago. So, for example, when we were looking at the closest stars to us, that 4 light years away from us, that's how they looked 4 years ago, not how they look today. And now we are seeing the universe as it was billions of years ago. And because of that, that means there's only so far that we can go. there's an edge to everything that we can see. And that edge is now all around us. This is what we call the cosmic microwave background, or CMB. Now, if we had a radio telescope and we could see in the microwave range of light, you would see this everywhere you looked. In fact, the first radio astronomers were very confused by this. They looked up into the sky with their telescopes and they were like, what is going on? Why are we seeing interference everywhere we looked? But soon they realized that it was actually something they were seeing out in space. This is a few 100,000 years after the Big Bang would have happened. So you can think of this as the baby picture of our universe, the very first light that we can see. But because this is the edge of everything that we can see, we can only go so far. This is the end of our journey. So we have to head back home. Now, if we were actually flying in space and we were actually flying the speed of light, it would take us about 13.7 billion years. But thankfully, I have our planetarium software, so it should only take us about a minute. But while we're zooming back home, I want to leave you with this one thing. Everything that we've seen so far, all the galaxies and stars, gas and dust, the cosmic microwave background, that's not everything in our universe. We have dark matter and dark energy, these mysterious substances that interact with light or gravity, they interact with light and our objects, but we actually don't see them. That's why we call them dark. And all of that dark matter and dark energy actually make up about 94% of everything that is out there. So everything that we have seen so far is actually only 4% of what we know that is out here. And that might make us feel a little bit small, like we're one little dot in this homogeneous universe. But I like to think of it this way. Yes, we're one little dot, but look at all that we have found, almost entirely by looking through telescopes. And there's a whole lot more for us to discover and a whole lot more for us to learn. So what makes it a wonderful time in human history? We're not just able to show this, take images with our beautiful telescopes, but I'm able to also show you our universe in 3 dimensions, which I think is pretty awesome. Well, we're starting to head back home to that third rock from the sun, the only place in all of this that we have actually found life. And that's pretty neat. So I want to say, welcome home, everybody, to our very precious planet Earth. And I hope you enjoyed our time here together on our tour of the universe. Thank you, everybody.